Hey, I just wanted to give a introduction to the earthquake lab that we're doing today. Um, so this picture here is showing you the model to keep in mind for Fourier transform. Remember in the first lab, we took 3 sine waves of different frequency and we summed them up and got this, strange but periodic wave as an output. So again, the axis on this horizontal axis is time, this vertical axis is amplitude, right? And at every point in time, it's just the sum of the amplitudes of these component waves. The Fourier transform looks at, tries to deconvolve or decompose this sum wave into the components that went into it. So when you run the Fourier transform, you would get 3 peaks at different frequencies. Now, so the Fourier transform is giving you an amplitude versus the frequency, and it's telling you the frequency of the waves that make up the sum wave. Okay, so one of the interesting applications of the Fourier transform is analyzing, lots of different waves, right? But so we looked at analyzing sound waves. We looked at analyzing data from sunspots, right, to figure out what the period frequency of the sunspots was. So what we're going to look at today is an application that involves earthquakes. So this is obviously a map of the world, and it has the yellow dots are the earthquakes that occurred in a 24-hour period. The size of the dots are scaling with the magnitude of the earthquake. So as you guys probably remember from earth science, taking that in high school at some point, that the surface of the earth is actually broken up into these different plates, and these plates are moving relative to each other, right? So it's a general field of plate tectonics. And the earthquakes occur most frequently at the boundaries between plates. So the plates are rubbing against each other, or one's moving under another, or they're splitting apart. This is now plotting up the earthquakes from 1900 to 2014. And again, you can see that they are located, not just randomly on the surface of the earth, but they are at the boundaries of all these tectonic plates. You do sometimes get earthquakes in the middle, right? So you actually see like the East Coast has some, which is, but there are these maybe minor faults, not the big plates that are outlined. Okay, so just another look at the tectonic plates and the type of plate that it is. So although we'll look in a second about what's happening at each of these kinds of boundaries, but it's interesting to note that this ridge here in the Atlantic is called the Mid-Atlantic Ridge. It's actually moving apart, right? So down in the south at 4 centimeters a year, up here at 1 centimeter a year. So the Atlantic Ocean's actually getting bigger, and South America and Africa are moving further apart. North America and Europe are moving further apart. In contrast, the Pacific is getting smaller. A lot of these are like subduction zones where one plate is going to move under the other. So, but this whole perimeter of the Pacific is known as the Ring of Fire, right, where you have some volcanoes and you have lots of earthquakes happening around the perimeter. Okay, so the motion of the plates is caused by convection that's actually happening in the mantle of the Earth. So the inner core of the Earth is very hot. The outer core is hot as well, too. And then we need heat to be transferred from that inner part to the surface of the Earth, right? It's trying to radiate outward. And the mantle is actually, there's convection zones that are happening in the mantle. So the hot material is rising, kind of moves along the surface, cools down, and then it will sink. So you get these convection cells set up. So again, hot here, moves, cools down, and sinks here. When it's a spot where the material is moving up, you get a ridge. The plates might be moving apart here. And then where the convection is coming down, the plates are drawn together. You can get one moving under another, and you get these trenches forming too. But regardless of the boundary, there is, when you start having these huge, ginormous things moving past each other, you get earthquakes. So this is just another look at that, the Mid-Atlantic Ridge, like I said, so that Atlantic is getting bigger. These plates are moving apart from each other. This is a view of South America where you have one plate moving under the South American plate. So when you have these subduction zones where one plate's going under, you often see these big mountain ranges there as well. And the trench, so really deep sea right off the coast of South America. Okay, so when an earthquake happens, there are two types of waves that are created. So the P wave is a compression wave, right? So you can think of this as like a wave rippling down a slinky, or sound wave is a compression wave. And you also get motion this way, perpendicular. So the wave might be moving this way, but then the material is oscillating perpendicular to it. So that's an S wave or a shear wave. And those are transverse waves. So longitudinal waves can go through, liquid, gas, but the transverse waves can't go through liquid. So it's actually, by studying earthquakes, is how we learned about what the interior of the Earth is made out of, that the outer core is actually liquid. So it's a little hard to see here, but you have an earthquake at the top. It's going to create P and S waves that are send out in all directions. When the S waves get to the outer core, they stop because they can't travel through the liquid. But you see the P waves actually will travel through. And so on this side, all this region over here, if you had, a seismograph stationed anywhere here, you'd be seeing the P waves and the S waves. If you had a seismograph over here, you would just be seeing the P waves because the S waves can't get through the outer core. Okay, so this is an example of what you see from a seismograph. So you get the P waves, they arrive first, the S waves come second, and then there's all these surface waves, which can be what causes most of the damage to the buildings on the surface. So this video just illustrates what a seismograph looks like, how it's working. So a P wave is coming, it bumps, right? And then an S wave. So the P wave came first with this little tremor, and then the S wave next. Okay, so in terms of the earthquake lab, what we want to think about is how these waves that are created by earthquakes can affect the structures that are on the surface of the Earth. And it all relates to thinking about natural frequencies or standing waves on strings. So I had you guys watch a video from PHYS to refresh on that material. So for example, if you have a wave standing on a string, or a standing wave that is created on the string is fixed at both ends. So there has to be a node, a place where there's zero amplitude at both ends. And then the waves that could be created on that string they can have different wavelengths, but they always have to have a node at the ends. So the longest wavelength, is, let me go back there, is this first one here, right, where you have a half a wavelength on the length of the string. And the red and blue is just showing you oscillating up and down. And this would be happening really quickly. But in this case, the length of the string would be equal to half the wavelength, right? Or the wavelength is twice the length of the string. Here's the next harmonic, where you'd actually get like a full oscillation, right? So this would look like a complete sine wave. And again, then you'd have the wavelength of this wave is equal to the length of the string, and then so on. You can keep adding these on. So some people think you have to like memorize equations for these, but really you can sketch these out and figure out the geometry, and then figure out how the wavelength relates to the length. The things that you need to know, though, would be like the waves on a string have to be fixed at the ends. If you are in a tube, like so these are all sort of your wind instruments, you can have some that are open at both ends. And then instead of having the node at the open ends, you have to have the antinode where it's at the maximum displacement. And again, you could sketch what the different possibilities are that always would give you the antinode at the open ends. And then finally, you can have some type of instrument like a pipe organ that might be closed at one side and open at the other. On the closed side, you need a node and then an antinode at the open side. And again, sketch it out and then think about how many wavelengths do you have in the length of the pipe, and then you can figure out what the wavelength is in terms of L. Okay, so every structure, not just these strings, but structures have their own resonance frequencies associated with them. And this is showing a demo. So basically, it's just a mass oscillating on between two springs, and there is a driving force there. So you can see that we'll see it in a sec. Let me just move that ahead. So it's going to just change the oscillation there. You can see that there's like a piston on the bottom that's oscillating the spring up and down. And then as he increases it or changes the frequency, we want to note what the amplitude of the motion is. So far it's not so big, but we'll get to the point where once you start driving it at the natural frequency of the spring, it's coming up here, then you'll get a very high amplitude motion. So now we're getting close to it right there. Okay, so right now the piston on the bottom is driving the system at the natural frequency. So you guys remember that springs have their own frequency associated with it, right? Square root of k over m. We've done harmonic motion. If you start driving it at that frequency, you get really high amplitude motion. Okay. Okay, so this is relevant. So structures like bridges and houses have natural frequencies associated with them as well. And so if an earthquake happens to, or some other natural phenomenon is exciting an object at its natural frequency, you get very high amplitude motion and you can have it collapsing. So these are just demo like shake tables where they're testing out different designs, but that's not looking good. Hard to get a sense of scale here, but these are like windows and stuff. So I think these might be almost full-size houses, which is crazy. Okay, and then this is a very famous example of resonance on the Tacoma Narrows. So there's just wind that happens to be buffeting the bridge at the bridge's natural frequency. You start seeing these huge oscillations that eventually lead to the destruction of the bridge collapses. Go a little further and then to go back and see that. It's pretty crazy. There's footage of people walking collapse right now. Okay. So the earthquake that we are going to be focusing on is one that actually occurred in Mexico. The damage that we're looking at is in Mexico City. So again, it's at a plate boundary. There was a earthquake, and then the waves obviously travel all around, and Mexico City endured a significant amount of damage. Okay, and yeah, so it's a magnitude 8 earthquake. We'll talk about that in a sec, but lots of information on Wikipedia if you wanted to read more about it. So it happened in 1985, before your time, but not before mine. So earthquake, the severity of them is measured on the Richter scale, right, with the magnitudes. So, can go from 2, let's say, up to 10. You hardly ever hear of 9. You guys will actually make plots to see, how often you get magnitude even above 8. This New Madrid, Missouri one is interesting, that 1812. I think that's the one that happened, and the Mississippi actually flowed backwards during that earthquake. The San Francisco 1906 was famous for the destruction again that inflicted. Northridge, California was another very famous one, very devastating. Who knew? I didn't realize this Long Island had one in 1884 too. And just yesterday there was one in Taiwan. It was I think a 7.4. And then this tells you kind of the equivalent energy release. But some of these, like over an 8, is like a volcano erupting, right, or a nuclear test. Okay, so Mexico City had this earthquake in September 1985, and the soil around Mexico City was like very sandy, and so it amplified the oscillations of the earthquake waves. It was devastating. Earthquake, over 5,000 people died. And what's interesting is shown in this bottom picture here, right? So there's some buildings that were left completely intact and others that were completely demolished. And it turns out that the buildings that were somewhere between 6 and 15 stories are the ones that were hardest hit. So we are trying to look at and understand why that is the case. Okay. And So just another example of a shake table, right? But there are these relationships in civil engineering that tell you what the natural frequency is as a function of the number of stories in the building, which you'll get to at the end of the lab. Um, but one of the things I ask is for you to think about how you might have to change building code. So here's a structure that's oscillating and obviously shaking more than you'd want a regular building to shake, right? And then here they're just adding additional supports that change the natural frequency of the building. And so now it doesn't oscillate as much as it did before. So something to think about, when we looking at the data for Mexico City, is there something they could have done in the building code or in how they specify, um, reinforcements and stuff to make it immune to the frequencies that the earthquake waves are generating?